Hello, my name is Alakh. I'm a student of third year engineering physics and I'm enrolled in the course PHN 313. This is my video PPT and the title of my video PPT is Elementary Signals. So first let us start with the introduction. Now there are several elementary signals that feature prominently in the study of signals and systems. The list is as follows. It includes exponential signals, exponential damped sinusoidal signals, step function, impulse function, ramp function. Now these elementary signals serve as building blocks for the construction of more complex signals. Now let us begin with our list of elementary signals. The first to come is exponential signals. Now a real exponential signal in its most general form is written as such. So x of t is equals to b e raised to the power 8. Here b and a both are real parameters. Now this parameter b is the amplitude of the exponential signal, which is measured at time t equals 0, because this will become 1. Now based on the sign of a, parameter a, whether it's negative or positive, we'll have two cases. One where we'll have a decaying exponential curve like shown in this figure, and one where we have a growing exponential curve as shown in this figure. Here, this figure shows the decaying exponential form of continuous time signal. It's continuous time signal. And similarly, this one is also continuous time signal, but here it's growing exponential form. Moving ahead, we'll have decaying exponential form of discrete time signal. And here, the growing exponential form of again discrete time signal. The previous one was, in the previous one we had continuous time signal. So moving on, continuous time. So for continuous time we'll have again three cases are there. One where a is equals to 0. So when a is equals to 0, if a is 0 will have a constant. So x of t is equals to c. It will be a constant signal. Now if another case arises when a is greater than 0, when a is positive. So when a is positive, we'll have a growing curve. So the exponential tends to infinity as t tends to infinity. Now another case when a is less than 0. So the exponential tends to 0 as t tends to infinity. Now here this value c, this is a constant, okay, and it's greater than 0. It's greater than 0, right? Moving ahead, discrete time. X of n is equals to p e raised to the power alpha n. Here both b and alpha again are real parameters only. So there are 6 cases to consider apart from alpha is equal to 0. So for one case is like when alpha is equal to 0, so we will have a constant signal. X of n is equals to p. Now when alpha is greater than 1, in that case we'll have a positive signal which grows exponentially. And another case when alpha is between 0 and 1. In that case, we'll have a positive signal only and it will decay exponentially. If alpha is less than 1, then the signal will, it alternates between positive and negative values and it grows exponentially. Okay, it grows exponentially. Another case when alpha is minus 1. In that case, the signal actually alternates between plus c and minus c, or plus b or minus b. Another case when alpha is between minus 1 and 0. In that case, the signal will alternate between positive and negative values and it will decay exponentially. Okay, it will decay exponentially. Now let us move on to another type of elementary signal, sinusoidal signals. So a general form of sinusoidal signal is as follows. X of t is equals to a cos omega t plus theta. Here a is the amplitude, omega naught is the frequency in radian per second, and theta is the phase angle. This figure right here shows the continuous time sinusoidal signal a cos omega naught t plus theta. Moving ahead. Now previous one was continuous time sinusoidal signal. So let's talk about the discrete time version of it. So the discrete time version of sinusoidal signal is written as such.
uh, x of n is equal to a cos of omega n plus phi. Okay, this is the discrete time version. Discrete time sinusoidal signal. Moving ahead. Now let's talk about sinusoidal and complex exponential signals. So what is a complex exponential? So this is the example of this is a complex exponential, e raised to the power j theta. Now here we'll use Euler's identity. So with Euler's identity, this e raised to the power j theta becomes cos theta plus j sin theta. Now complex exponential signal is written as such: b e raised to the power j omega t. Here b is actually e raised to the power j phi. So this entire complex exponential signal becomes a e raised to the power j bracket will have phi plus omega t. Actually j is also common. J will take common over here. So it becomes, again we'll use the Euler's identity only, and it will become a cos omega t plus phi plus j a sin omega t plus phi. So if we talk about the real and the imaginary parts, so it will become, so the real part of this complex exponential signal is actually a cos omega t plus phi, and the imaginary part is this, a sin omega t plus phi.
So if we talk about the coordinate time sinusoidal signals, so this is coordinates. X of t is equal to a sin omega t plus phi. The real part of the complex exponential signal is also coordinate time sinusoidal signal, and so is the imaginary part, a sin omega t plus phi. And if we talk about the discrete time case, then the real time, the real part of the complex exponential, but the discrete version, the discrete time version, b e raised by j omega t, here a cos omega n plus phi. This is the discrete time, and so is the imaginary part of the b e raised by j omega t, complex exponential sinusoidal signal, but the discrete time version. So let's move on to another elementary signal, exponential damped sinusoidal signal. So how do we get an exponential damped sinusoidal signal? If we multiply a real value decaying exponential signal, a real value decaying exponential signal with an with a sinusoidal signal, then this will result in an exponential damped sinusoidal signal. So as you can see, x of t is equal to a e raised to the power minus alpha t plus sin omega t plus phi, where alpha is greater than 0. Here a sin omega t plus phi. This is the coordinate time sinusoidal signal, and e raised to the power minus alpha t is the exponential. So, and it's the decaying, because alpha is greater than 0, and here we have e raised to the power minus alpha t. So it's the decaying exponential signal. Hence we call it exponential damped sinusoidal signal. So this is the figure. This shows the exponential damped sinusoidal signal. Here a is actually 6c and the value of alpha is 6. Now as you can see, like in this figure, with increase in time, the amplitude or the sinusoidal oscillation, you can see that it's decreasing. It decreases in an exponential fashion, and finally it approaches to 0 as t tends to infinity. So this is the exponential damped sinusoidal signal. Now let's move on to step function. So the discrete time version of the unit step function is defined as u of n, where n is greater than or equal to 0 will have a value of 1, and when n is less than 0, will have value 0. So its figure looks something like this. This is of unit amplitude, hence 1. So discrete time step function of unit amplitude. If we talk about the coordinate time version of the unit step function only, then it will be u of t is equal to 1 when t is greater than 0. And u of t is equal to 0 when t is less than 0. Here, this figure shows the coordinate time step function of unit amplitude.
Now there is a discontinuity. There is a discontinuity which exhibits at t equals 0, and the value of u of t, the step function, it changes instantaneously from 0 to 1 when t is equal to 0. That's why we say that at t equals 0, u of t does not exist. Okay, it's undefined. Now moving ahead, we have impulse function. So the discrete time version of the unit impulse is defined as delta n when n is equal to 0 is equal to 1, and when n is not equal to 0, for any other value other than 0, we have delta n to be 0, equal to 0. This can be seen, which is also shown in this figure. So this is the discrete time form of the impulse function. So this is the graphical description of unit impulse function delta n. Now if we talk about the continuous time
version of the unit impulse, it is defined by the following pair. So here the condition are delta t is equal to 0 when t is not equal to 0. Okay, so when t is not equal to 0, it should be 0. And for if we integrate from minus infinity to plus infinity this function, this delta t with respect to time, then it will come out to be 1. Okay, so this is the this gives us the continuous time version of the unit impulse function. Here delta t is also referred to as the direct delta function. Moving ahead. Now, in order to get a better intuition, okay, to understand impulse function a little better, what we can do is we can imagine, okay, we can imagine a rectangular pulse, okay, where each pulse has a width of epsilon and has a height of 1 over epsilon. So we can say that the area is 1. Why we took this width? Why epsilon and why height is 1 by epsilon? Why we want area to be 1? This is because we defined impulse function as such. We want that when we integrate from minus infinity to infinity, this function with respect to time, it becomes 1. So the area, that's why we want the rectangular pulses with area 1. And the unit impulse, what will it be? It will actually be the tallest one, okay, the quintessential tall, the tallest one and the most narrow pulse. Okay, it will be the tallest and the most narrowest pulse. If you can imagine that, that will be the unit impulse function. So that's the unit impulse function for you. Let's talk about ramp function now. The integral of this step function, u of t, is a ramp function of unit slope. So r of t, you can say, okay, so r of t is, when t is greater than or equal to 0, it is equal to t. And for t less than 0, it is equal to 0. Or you can say, since it's the integral of the step function u of t, so you can say that r of t basically comes out to be t into u of t. Now, if we talk about the discrete time version of the ramp function, then r of n is basically n. Okay, it is n when n is greater than or equal to 0. And when n is less than 0, it is equal to 0. Or you can say that r of n is actually n u of n, So this is the discrete time version of the ramp function. Now, let's do something, let's do a successive integration of unit impulse function. Okay. Now, when we do successive integration of unit impulse function, it actually yields a family of functions. First, you have unit impulse, okay, delta t you have. So if you integrate it, you will get unit step function, u of t. When you integrate step function, you get unit ramp function, tu of t. When you integrate this with respect to time, on time actually, you get unit parabola. And so on, you can keep on integrating. And thank you. That's all.